us about fixed point properties. Yes. Okay, so I want to thank the organizers for the invitation and for Evan for covering for me because I got stuck in traffic. So if I understood the assignment correctly, I should give you a group, a graph, an operator, and a spectral gap. So I'll try to do everything. Let me start with the groups I want to consider. So they already showed up in Taka's lecture, but let me remind them again. I want to consider universal lattices, which are groups of the form here and the P1 to Pm, where this is just the group generated by, so let me just from now on denote this string in R. M is some fixed integer. And this is just the group generated by the elementary matrices, where an ij elementary matrix is 1 here and p here, and so this is the ith row and the jth row. So another group I want to consider, which this group will be a quotient of, is what's called the Steinberg. So let's denote it STN over the same thing R. And basically it's the group where you just take these, you think of these as generators, but you take only the Steinberg commutator relations. So let me be specific. So the generating set will be xi, j, p, where p is in my ring R, and the relations will be these three relations. First of all, xij p1 multiplied by xij p2 is xij p1 plus p2. Second, the commutator of xij p1 with xjk p2 is just xik p1 p2, p1 times p2, and I assume here that I is not k. And the last relation is that if you do a commutator of xij p1 with xkl p2, it is trivial if you're not in the previous cases. So if k is not j and I is not. So it's basically, if you remember Piotr's talk, we basically forgot one relation. And so this is called the Steinberg group, but it's actually the Steinberg group over the root system A, and there's a generalization of that, the Steinberg group over some other root system. I don't want to get into that right now, maybe in the end. Okay, so that's my groups. And now I want to talk about fixed point properties of these groups. So I want to define a property which I'll call property FU. Sorry, UC. Property FUC. So UC is for uniformly convex, so just that we are on the same page. So if I have a Banach space, it is uniformly convex. and let me abbreviate UC. If for every two unit vectors, C and eta, sorry, I forgot the, okay, if there is a function delta called the modulus of convexity from 0 to say to 0, 1, not including 0, such that for every two unit vectors, if you have that their distance is greater or equal than epsilon, then the norm of their midpoint is less or equal than 1 minus delta epsilon. And the mental picture is that, okay, your circles are round, so if you have 2 points that are far apart, their midpoint will sink in at least delta epsilon, where epsilon is this distance between them. So it's a very nice property. It was mentioned in at least one talk before. And now let me state my fixed point property I want to define. So we'll say that, so here's the definition. Gamma has property FUC if for every uniformly convex Banach space and every affine isometric action of gamma on your Banach space, it holds that you have a fixed point. So let's call this action rho and let's denote it like this. So no matter what uniformly Banach space you give me, no matter what affine isometric action, there must be a fixed point. So this is a generalization. Oh, I should have said, if you don't know uniformly convex Banach spaces, so the first example are Hilbert spaces, and the second example, I guess, is LP spaces, where P is between 1 and infinity, and non-examples are L1 and L infinity. Okay, so after I said that, you can see that this is a generalization of property FH, right? So generalization of property FH, which says that for every affine isometric action on a Hilbert space, you have a fixed point. So this is strong, right? Okay, but I should just mention that all these fixed point properties are preserved under quotient, so if the groups I consider are those, it's enough to prove for the Steinberg group, and it will follow for the universal lattice, okay? Okay, so let me give some examples and non-examples of groups with these properties. So, the silliest thing is finite groups, right? So, finite groups, but that's cheating. Now we got to the more sophisticated. So these are the examples of group that has this property. So another example is the groups SL and Z for n greater or equal than 3. So this is due to myself and the Latin de la Salle. And even, let me not write, but just say, even more generally, it holds for higher rank semi-simple groups and lattices over any local field. What are some, and that was a really group effort. So the non-Archimedean case is due to Laforgue and Layou, and then the real case is due to myself and the Latin de la Salle really solved the problem completely. Okay. So what are some non-examples? So groups without T, because we said that this is a generalization of property FH, which is equivalent to property T. So if you take a group that doesn't have property T, that it won't have this stronger property. And also, as was mentioned yesterday in Jan's talk, a hyperbolic. Because these always act without a fixed point on some LP space where P is large enough. Okay, great. Okay, let me just maybe mention the brief history regarding property T for these groups, because even property T is a non-trivial result. So property T for, say, SLN was known basically, like, known to Kashdan, right after he defined property T. But property T for universal lattices is due to, let me get the year correct. So it's due to Shalom and Wasserstein. In 06. And property T for STN is due to Ershov and Daikin in 2010. So you can see it's a non-trivial issue to pass from the, even for property T, to pass from the results we know about SLNZ to these more general groups. Even for property T, it looks like 40 years. Okay, so now I want to give you, to state my result.
So to refresh my memories, the kernel of the map from Steinberg to ELN is K2.
Yes.
Okay. So that's an issue. Okay, so it's an issue.
No, but it's really different problem, because this was done by sort of some bounded generation argument, not the trivial one, but basically some bounded generation argument. And here you do not have this. So Ershov and Daikin solved it some way, and I should say Mimura also solved it in a different way, avoiding again the bounded generation. Okay, so let me maybe state the result I'm aiming for. So this is mine from 23. So both ELNR and STNR, where n is greater or equal to 3, have this And the proof basically has two components. So, and okay, I should say, maybe not right, I can also do it for almost every other Steinberg group over a spherical root system, except for the C2K. So if it means anything to you, you know, if not, you can forget. But I said you have the Steinberg groups.
Sorry, what are your assumptions on the ring? What are your assumptions on
Rank at least 2.
The ring.
The ring is that one.
Okay.
The Z, basically any finitely generated unit of ring, of course.
commutative?
Commutative, yes. Right, that's an important one. Okay, great. So the proof has 2 components. So ideas. So first there is a relative fixed point property argument, and then there's what Mimura called the synthesis argument. Which is a way to say if I know some relative fixed point property, can I get the fixed point property for the entire group? So let me focus about this in this talk. Okay, so now let me maybe define explicitly what is this relative property and state my relative result, and then let's talk about what goes into it. Okay, so the relative thing is exactly what you think it is, but let me spell it out. So definition, if you have a group gamma and a subgroup K, you say that gamma K has relative FUC if for every uniformly convex Banach space and every affine isometric action of gamma on that Hilbert space, there is a fixed point of the subgroup. So that's what relative fixed point means. And the result I want to tell you about is for STN3. That's basically all I need to make everything work. So here's the theorem. Again from 23. It says the following. Let's take gamma to be ST3R. And let's take K to be the group generated by X12P and X23P is in my ring. And okay, it's we want generality, but it's easier to draw matrices. So what is K if I?
So SIMP. SIMP 5.2.
No. Just generated by. Okay, let me. Okay, I want this in the context of the universal lattice. So no saying P, right? So P1. Everything that's generated by this and this, and so you get this, basically this copy of the Heisenberg, okay? And the theorem is that this pair, gamma K, has this relative fixed point. So every action of this group on a uniformly convex Banach space, this copy of the Heisenberg group, we'll talk about in a minute, admits a fixed point. Okay. So this is where graphs and spectral gaps come in. Great. Let me do a detour to graphs. So even if you lost me completely, I'm going to tell something that's slightly unrelated and then come back to my story. So you can join at least for that part. So let's let Q be some prime. So an interlude about spectral gaps in graphs. So let Q be some prime, and let's take the Heisenberg group over FQ, which is just the group 1, 1, 1, X, Y, Z, where X, Y, and Z are all in the field FQ. So just this Heisenberg group with these field entries. And let me describe you first a graph. So let me describe a bipartite graph coming from this group. So I have two sets of vertices. So Vx are cosets of the form G and this subgroup. Vy are cosets of the form G. This subgroup, and let me give you the edges. When do you connect? You connect G with this subgroup, with say G prime, with that coset if and only if what? Definition, the cosets intersect. So this gives you a bipartite graph. You can show that the number of vertices on each side is Q squared, and you can show that it's Q regular. So this is Q regular. There's another way to say this graph, not maybe this complicated way. You can say it like this. Take the projective plane over FQ. You have points and lines. You can take the incidence graph, right? The graphs where one side are lines and the other side are a point, and you connect wherever a line passes through a point. Now throw one line with all the points on it, and one point on that line, and all the line comes out of it, and you'll get that graph that's sometimes called the biaffine graph. And this graph has the spectrum of the simple random walk. On this graph is, let me do contain because I'm not sure about 0. So it's bipartite, so it always has plus or minus 1. And the second largest eigenvalue is 1 over square root of Q, and maybe also 0.
Spectral graph here very different from the one for the affine space or the projective plane?
Yeah, I mean, not very different, right? The projective plane is 1 over square root Q. I mean, it cannot be. It's like almost everything, right? So it's similar, but not the same. And okay, so another way you can say this this fact that the second largest eigenvalue is 1 over square root of Q, you can say it in terms of representations of this Heisenberg group. So let me restate this claim about the second largest eigenvalue. And here's, I promised operators also. This is a graph, let's do an operator. So let's take pi, a unitary representation of this group without non-trivial invariant vectors. And let me define two operators in the two elements in the group ring. So let's denote capital X to be this averaging in the group ring, 1 over Q, X in FP, FQ, sorry, 1, 1, 1, X. So that's one element in the group ring. And similarly, let's do the average along the Y thing. And saying that the second largest eigenvalue is 1 over square root of Q is exactly the same as saying that if I take phi x, y, its norm, again, I assume that pi does not have any invariant vector, any non-trivial invariant vector, its norm will always be less or equal than y over square root of Q. So it's an exercise, it's some work to see that saying this for every unitary representation, you can take the regular and throw out the invariant, is the same as saying the second eigenvalue fact, but you can work it out. It's not that bad. And now I want to take this example and make it to another graph, which will play a role, or which the idea of it will play a role.
Do you know the girth of this graph?
It's like 4 or something. Oh, no, the girth is 8, sorry, the diameter is 4. Okay, so let me give you a different graph, which is maybe a generalization. So fixed to integers, dx and dy. And let's consider h of dx and dy to be now, again, some Heisenberg group. But now my entry is x, y, and z are all polynomials over fq, and the degree of x is less or equal than dx, and the degree of y is less or equal than dy, and the degree of z is less or equal than this. Okay, so instead of putting just fq, I'm putting polynomials up to certain degrees. Great. So you can check that this is indeed the group. And now you can form the same, okay, so you can form basically the same graph, doing this as coset and this as edges. Or you can form basically the same averaging or groups in the elements in the group ring, sorry. And you can ask, so what's the second largest eigenvalue here? So we should have gained something because we increased the degree, right? But if you just look at the second largest eigenvalue, you still get this 1 over square root q, because this graph basically projects on, where is it? On this graph. So you cannot, just looking at the second largest eigenvector, it doesn't say you increase the degree, but it doesn't seem you benefited. But, and that's the nice part, previously the spectrum was just these things. Now you got many more other eigenvalues. So let me just write x of dx as before. And x dy as before. But now let me add x dz, which is not averaging over everything, but up to some degree. So z dz is 1 over q dz plus 1 sum z fqt. The degree of z is less or equal than dz, but now I do not want to take dz to be everything, to be the sum. I want to consider dz to be lower. And now with the magic, if you take that statement and do, again, pi as before, and do x dx, and now z dz plus 1 minus z dz, and y y, and take the norm, and we assume following.
Sorry, in definition of z, what's in the sigma?
The central matrix.
This, thanks. And let's assume that I take dz, which is larger than the minimum between dx and dy. But okay, it's smaller than the sum. So some number here. So what you get in the norm, so now see I restricted the norm. I'm basically thinking about some subspace, right? I restricted the norm to consider this random walk, but on some subspace. So what you get is actually something of the form, let's do distilled up to universal constant, because I don't want to worry about being plus or minus 1 wrong. 1 over square root of q, the minimum between dx, dy, and dx plus dy minus this. So you can think about what if all these numbers are some d, some fixed d large. So you basically get everything to be equal d here. So you can see you get better spectral gaps, much better than the trivial ones, than the second largest eigenvalue, if you restrict to this subspace.
Can you say what is in the difference? What is the difference?
dx plus dy minus dz. The difference between the
in the operator, it's c
it's
subscript d.
z dz plus 1, averaging over plus 1 minus dz.
Okay, it's not in the exponent. It's
No, it's not. It's like this. What that
okay.
component.
Okay.
Oh, thanks. Okay, so I should say that this sort of improving spectral gap, you won't find it if you read Laforgue's paper of Banach's strong property T, but it's buried there. That's why it makes the whole thing tick. But it's really buried. You need to look for it. So now the amazing thing, and that it works even, so here everything was nice, because basically once I have polynomials over a finite field, I can sum over everything and you basically just get projections. Now the amazing thing is that this works even if you try to average over our group R. So let me give you the statement. So here's the thing. And it will look technical. I will write it and then discuss what it means. Okay, don't be alarmed. So let's take gamma to be our group ST3 and let me write the T1 to Tm. And let's take a copy of the Heisenberg group in it. So think about it, again, it's easier to think about EL3. So now I want to, so this, you see a copy of the Heisenberg group in it. And now I want to define averaging operators, similar to the ones I had here, but since my ring is this thing, I cannot average on all coefficients. I need to take some ergodic averages. So let me define x of d. Oh, first of all, sorry. I need to introduce sorry. I want to define what do I call polynomials of degree d, not really of degree d. These are all the sums of the form t, which is a monomial, which means it's t1 k1 to tm km of degree d, of degree less or equal to d. And I want to take a combination of these monomials, and now AT is always a number between 0 and 2 to the power of d minus 1. So take all these polynomials where the degree of all the summands of everything is up to d, but the coefficient multiplying it is between 0 and 2 over 2 to the power of d minus 1. So again, in finite field, you have an easier life because you can just sum over all the field, but now we are with z. So, and now if I look at these polynomials, I want to define what is my x. So my x, let me carry this notation, but think about it here. So my x is 1 over the number of these d polynomials, the set. Sum p is such a d polynomial, 1, 1, 1. So it's similar to what I had before, but now since my coefficients are in Z, I need to take this sort of, it's like averaging over Fellner sets, right? It's a larger and larger Fellner set. Okay, but I see I started the theorem and then I got a little messy. In my notes it's better, obviously. Okay, but let me give you the theorem. So this is, this is X. Right? And you can form YD and ZD the same. These are all elements in your group ring. And now the theorem is that for every E uniformly convex, and there is some constant R between 1 and 0 that depends on E, such that for every dx, dy, dz with dx plus dy greater than dz, and dz greater or equal than the minimum between dx and dy, and for every affine isometric action of our group ST3 on E, we have this. So now I'm not doing pi, I'm doing rho, but we have a similar behavior. We have this rho of x dx, z dz, y dy. Oh, and so and for every C in E, say unit vector. A lot of quantifiers. I told you it's there. Acting on C minus rho of almost the same thing, but adding one here.
What's the conceptual difference between pi and rho? This is linear or affine?
This is affine.
Fine, okay.
It's also true for linear, but we're doing affine. So the norm of this, which is almost the same as the norm of that, but since I'm doing rho, I need to do it like this, is less or equal up to some universal constant by dz to the power of, say, 10m times r to the power of square root of the minimum of what we had before. So it's not as good because we have this square root, but basically the minimum of dx plus dy minus dz and dx and dy. So this comes from the fact that since we are doing an isometric action, the norm, even if we started with xi of norm 1, the norm of xi can increase, but it doesn't increase too badly because we have a good control of the word norm.
What is m in the exponent of dz?
Minimum?
No.
What did I mess up?
You have 10 times m.
Ah, yeah, 10 times m. M is this m of the number of.
Okay. Oh, I see.
Yes.
So what is the modulus of uniform convexity? And this is a statement
Ah.
of uniformly convex spaces.
This depends on E and actually depends on only on the modulus of uniform convexity. The worse your modulus is, the closer to 1 you are. Thanks.
And what is the significance of the norm 1 of psi? I mean, it could be.
It could be, I
Something
mean,
bounded.
just
I mean,
fix
you
the
want-
norm because the norm will, up to, the universal constant will depend on the norm. It doesn't really. I just, okay, psychological reasons, okay? Okay, so I see I won't have time to explain how to use it, so but maybe let me explain what it means and then hand wave about how it's used. So if you're a little like me, whenever you see some extremely technical statement, you say, okay, I'll wait to the conceptual part, it's not that thing, but I claim it is this. Because this is what makes the whole thing tick. And in opposition to what Zhuk did, and what Garland did, and what Piotr told us, and what Taka told us, this is not looking at the spectral gap only at some closed ball or only at some near neighborhood. This is looking at a sequence of improving spectral gaps, the larger and larger you average. So, and this is very much inspired by the work of Lafort, because that's exactly what he did. He found like spectral gaps in all scales and utilized them. So, and this is, I mean, I don't know to do it any other way. I don't know how to go to all uniformly convex with only, say, one spectral gap. As good as it is, I really only, I mean, in the literature, I think there are really only proofs if you want to do everything with better and better spectral gaps on larger and larger scales. So, so I should say, even for Z, which I did before this, like all the proof waited for this. I know all the proof scheme a month before I could. Even for Z, you take the same averages, but you don't have T there. Just take averages on the internet. I know everything apart from, I almost gave up. Because I know what to do once I get this, but getting this is really the hard part. Getting this better increasing spectral gaps. So how do I use it without just hand wavy, without giving you really the details? The way I use it, and I'll finish there. It's a very neat idea, but I don't have time. You can basically, you have, let's talk about EL3. You basically have 6 copies of the Heisenberg group inside EL3. You have this one, you have this one, you have, okay, continue. And the way I do it is I basically multiply all these averages in order that each time that I all these 6 averages, in order that each time that I multiply, I see a Heisenberg group. So let me maybe do the diagram. I don't know if it will help. I start with averaging here. This is my x, do xd, and then do zd, and pass to here, and pass to here, and pass to here, and pass to here, multiply this, all these averages, and now, if you look at the first 3, you see Heisenberg group. So you can use this thing to up the set on which you average z. And now, if you go here, okay, it's messy, but again you see a Heisenberg group, and again you can, paying a small price in the norm, say I can average this on this subgroup on a slightly larger set. And then you basically work out how much do you pay, and you can see that paying decrease the series convergence, paying a converging price, you can get averaging to infinity, right? Like averaging on this entire group or on this entire group. So that's the way you do it. It's slightly technical, but it can be done. I can show it to you afterwards if you want. Okay, let me just not say another word. Let me stop it.
You gave a talk about actions of a group on uniformly convex spaces.
Yes.
I never saw where uniform convexity enters the picture. What does uniform convexity do for you?
It allows me to prove it.
But why? I mean,
Why does it? You know? Okay.
What is the role of uniform convexity?
The role of uniform convexity is that if you average stuff that are far, you can control how much smaller they become. So the way I do this is, okay, very simplifying, is saying, okay, but you can make it into this commutes, but make it into these things should move this difference at least that much. And that's why it converges at least something. But, okay, I'm lying, because not these things, I break it up to different averages, but I make like a sequences of averages, which I show that each one of them move at least something, and then I can, by uniform convexity, I can control how much it shrinks. So that's why I get this R to this messy power, but that's the idea. If you know that if your groups, your element in the average move you that much, the average will decrease your norm this much. That's the vague idea.
So, as a speculative question, if instead of having uniformly convex space, we took a space of non-trivial type, would you have any hope?
I had hope coming into this problem, but yeah, I worked tons on non-trivial. I mean, it should, morally, you shouldn't have this square root, and it should work for non-trivial type. I couldn't, I mean, I spent like many hours. I couldn't get it.
So these estimates in this finite group that you attribute to Lafort, they allowed him to prove stronger statement than what you had.
Yes, my stronger statement, right.
Do you see any way of using your estimates to obtain something?
No, but that's another problem which I wasted. I don't know if wasted, but I spent like many hours on it. In Lafort, you can just do, he does this whole average at once, not in steps. And then you can do something much better. You can say, I'm not thinking about, say, isometric action. I'm thinking about slowly growing action. But I couldn't do it. I need to do it in steps. And when I do it in each time, I take like some part of the average here and bound its norm, and then takes another part and bound that norm. And once you do it like that, I mean, you cannot go to Lafort's strong properties.
Can you design, given your proof already, can you design a slow enough growing norm action that fits?
Actually, no. That's the. I thought about that as well. No, that's the annoying part. I really need isometric.
All right, if there's no other questions, I think I can.